Alright, our last example is the die game problems. So the game is you roll a die. If it comes up a 6, you win $100. If not, you get to roll again, and if you get a 6 the second time, you get $50. If not, you lose and you get $0. So we're going to create a probability model for the amount we would expect to win, and then we're going to find the expected amount. So, three options. We could win $100, we could win $50, or we could win $0. This time, though, to find these probabilities, I don't really need to make a table. I'm just going to think about how a dice works. So to win $100, I have to get a 6 the first time I roll the die. So there's 1 6 on a die, out of 6 possible sides it could land on. So 1 out of 6 is our probability, and I'm just going to leave it like that. You could put it as a decimal if you wanted to. To win $50, that means I got not a 6 the first time and a 6 the second time. So there are 5 sides that are not a 6 on a die out of 6 total, and means I multiply, and then there's 1 that is a 6 out of 6. So not a 6 the first time, and then a 6 the second time. So 5 over 6 times 1 over 6 is 5 over 36, which again you could leave as, or you could put as a decimal. I'm just going to leave it as a fraction. And then to win $0, that means we got not a 6 both times. So 5 over 6 times 5 over 6 is 25 over 36. And then to find the expected amount, well, that means that I'm doing my mean formula. So 100 times 1 over 6 plus 50 times 5 over 36 plus 0 times 25 over 36, which if you do that, you end up with about $24. If you do the standard deviation formula, you get about $38. Okay, so the next question is kind of an extension of our die game problem. What happens if we double the dollar amounts? So doubling the dollar amounts means instead of 100, I have 200, instead of 50, I have 100, instead of 0, I have 0. And that means that we are doing the expected value of 2x and the standard deviation of 2x. So that's just the scalar rule. 2 times e of x, 2 times 24 is 48. And then 2 times standard deviation of x, 2 times 76, 2 times 38 is 76. But if we play the game twice, that's a little bit different. Playing the game twice means I keep the amounts the same, but I'm just doing it twice. So that's like saying x1 plus x2 as opposed to 2x, and that's a little bit different. So for expected value, we're just going to do e of x plus e of x, so 24 plus 24 is 48. That's the same as what we got for the 2x one. But if I do the standard deviation, I have to treat it as 2 separate random variables. So square root of 38 squared plus 38 squared comes out to about 54, which if we'll notice is different from what we got when we did the 2x. So our mean stays the same whether we double the dollar amounts or play the game twice. But our standard deviation changes. Our standard deviation goes down a little bit. And this, of course, the standard deviation part of it, we have to assume that each play is independent, because when we're doing the 2 different random variables formula, standard deviation and variance, we have to know that they're independent, and that's important. Okay, so just for kicks, what happens if we play the game 200 times? Well, for e of x, it's just going to be 24 plus 24 plus 24 plus 24, etc., 100 times, or 200 times. So 200 times 24 would be our answer. But for standard deviation, I have to treat it as all different random variables. So 38 squared plus 38 squared plus 38 squared plus 38 squared, etc., which I could write as 200 times 38 squared, square root of, which if I take my basic algebra skills, we could know that that's square root of 200 times 38. And you could get your answer from there. Again, assuming that all the plays are independent of each other. And that's the end of the lesson.